Problem 30 says when 85 milliliters of sulfuric acid, and it gives the density of sulfuric acid, reacts with excess aluminum hydroxide, how much water is produced? So in any stoichiometry problem, when we're not given a chemical equation, we need to start out by writing one. So I know that sulfuric acid's formula is H2SO4, or I can get that by crisscrossing H plus with SO4 minus 2 to get H2SO4, and that's reacting with aluminum hydroxide, so I'll crisscross aluminum, which has a +3 charge, with hydroxide, which is OH minus 1, AlOH3, and so I know this is going to be a double replacement reaction. So on the product side, aluminum is going to cross with sulfate, so Al2 SO4 3, and then my other product is just going to be hydrogen bonding with hydroxide, which I know will create water, and I'm going to write that as HOH. Then of course I also need to balance my reaction, because I know we can't do stoichiometry until we have a balanced chemical equation. So I'll put lines out front of each of my reactants and products. The first thing I notice is the imbalance of sulfates, so I'm going to put a 3 here. So I have 3 sulfates on both sides. Now I have 6 hydrogens on my reactant side, so I'm going to put a 6 in front of HOH. That also ends up with me having 6 hydroxides, so I need to correct that on my product side by putting a 2 in front of aluminum hydroxide. And now I have 2 aluminums, but I already have 2 aluminums on my product side, so I'm just going to fill in a 1 to remind myself that this is fully balanced. Now that I have a fully balanced equation, I can actually start to look at my stoichiometry here. So I'm starting with 85 milliliters of sulfuric acid, which isn't even on my chart, but I know that I can use my density value to convert my milliliters to grams. So I'll convert my milliliters to grams, so I'm kind of starting up here on my chart, and then I need to, it says how much water is produced. So I know it's a different substance, but it doesn't specify a unit, so I'm going to go to the closest thing, which is moles of my other substance. Since it doesn't specify whether it needs to be grams or liters or moles or particles, I'm just going to go to the closest thing that will get me into my new unit, and I know that is the mole. And so I'm going to have, let's see, one step to get me from milliliters to grams, then grams to moles of my same substance, and then moles to moles of my new substance. So this will be a 3-step problem here. So let's start out. 85 milliliters of sulfuric acid, H2SO4. I'm going to put that over 1. First, I'm going to take my milliliters to grams. Then I will take my, and I forgot a substance there, so I should go back and fill that in. Let's see, milliliters of H2SO4 to grams of H2SO4, and this is important here because the density is not the same for all substances. Then I will take my grams of H2SO4 to moles. There's my second step, and then finally I'm going to end with my mole to mole steps, so moles of H2SO4 to moles of my new substance, and in this problem it's asking me to find the amount of water, so I'll go to moles of water. Okay, so I have all of my units and substances set up. Now I just need to plug in some numbers. So for my grams and milliliters, I'm going to use the density value that was provided in the problem. So 1.83 grams per milliliter. So 1.83 grams in every 1 milliliter. For my moles to gram step, I know I'll put a 1 next to mole, and I know that 1 mole of H2SO4 is going to be equal to the molar mass, so I'll just add that up real quick. So let's see. Hydrogen has a mass of about 1, so 1 times 2 plus the mass of sulfur. And so if we look at a periodic table, that's about 32.07. And then the mass of oxygen times 4, so 4 times 16. And when I add all that up, I get about 98.07. grams per mole. So that's what I'll substitute in here. That's the number of grams of sulfuric acid in 1 mole. And then last but not least, I need my mole-to-mole ratio, and I know that comes from my balanced chemical equation. So my moles of water to go on top, that'll be 6, and then moles of sulfuric acid, that's going to be 3. And it is important that you don't simplify here. We want the coefficients that are shown in the chemical equation, so it's clear to whoever's reading the problem where those values came from. So don't simplify. We have all this in here now, so our last step is just to multiply across the top and divide on the bottom. So I'm going to type in my calculator, 85 times 1.83 divided by 98.08 times 6 divided by 3. And when I hit enter here, I got 3.1719 with some other numbers on the end, but I know that I only actually need to keep 2 significant figures because my given value of 85 only has 2 significant figures. So here, let's get a different color, and I'm going to keep the 3 and the 1 and then look at the next digit over to figure out whether I'm rounding up or staying the same. And the 7 is going to make that 1 round up to a 2, so 3.2 moles of H2O is our final answer. And if you went all the way to grams, or if you went to liters of gas, since it is, oh, no, not liters, you can't do liters of gas actually. If you went to particles of water, that would also be fine. The only thing that wouldn't be fine actually would be liters of gas, because water in this case is not going to be gaseous since it's not a combustion reaction, and it doesn't specifically say that the water is gaseous. Usually, well, in an acid-base reaction we rarely end up with a gas. Next we have a reaction where a student burns 0.25 liters of propane, and it gives us the density of propane. With excess oxygen, what volume of carbon dioxide is produced? So because they said there's excess oxygen, we know that this is an ideal stoichiometry problem. We don't need to worry about the amount of oxygen. We don't need to find the limiting reactant. We are to assume that there's plenty of oxygen. So we'll start with kind of outlining our strategy. 0.25 liters of propane. That liters is not the liters on our mole conversions chart because propane is not a gas, it's a liquid. If you weren't sure of that, you can know that by the fact that it gave you the density value here. So we need to take our 0.25 liters and get it to grams. We don't have our density in grams per liter, so I'll first need to kind of step this to milliliters, and then from there we can take the step into grams using that density value. So we're starting kind of up here on our conversions chart, not even on the chart to begin with, a few steps away, and then it's asking us for volume of carbon dioxide, so volume of an entirely different substance here. So I'll find liters on the other side of my chart, and this time it is the liters on our chart because carbon dioxide I know is a gas, and so we're producing a gas here, so it is liters, meaning 22.4 liters equals 1 mole. So this is going to be a whole lot of steps here. So let's start by kind of counting those. So one step, liters to milliliters, milliliters to grams, grams to moles, moles to moles, and then moles to liters. So 1, 2, 3, 4, 5 steps here. So this is going to be a long dimensional analysis series. That's okay. We're just going to start at the very beginning and work our way over. So we'll start with our 0.25 liters, and I'm first going to convert liters to milliliters. And I know that 1 milliliter equals 1,000 milliliters. 1 liter equals 1,000 milliliters, and I don't need to put a substance here, although I should put it on my given value. I don't need a substance on my liter to milliliter conversion because there are always 1,000 milliliters in a liter. It doesn't matter what substance I have. Now, on my given value, I do need to put propane's formula, and I know that propane is C3 H8, but if you didn't know that because you're in introductory chemistry, that's okay. You can ask your teacher or just Google the formula for propane if you're not sure. On a test, it would certainly be given to you as C3H8. So there's our first step, our liters to milliliters. Now we need to take our milliliters of C3H8 to grams of C3H8, and that'll be our density value that we'll use to get that. Then we will go from grams of C3H8 to moles of C3H8. Then we have our mole to mole step, so our moles of C3H8 to moles of our new substance, which in this case is carbon dioxide, CO2. Then we have our final step, which is our moles of CO2 to liters of CO2. So it's a whole bunch of steps here, but not too bad. So I know that anytime I see mole that's not in a mole to mole ratio, I'm going to put a 1. So I'll put a 1 on the bottom of my last conversion factor. I will put a 1 on the top of my gram to mole conversion factor. And then I think that's all for the moles. Now we'll start by figuring out how many grams are in a mole. So C3H8, I'll need to add up that molar mass. So 12 times 3 plus 1 times 8. So when I add that up, 36 plus 8 gives me 44 grams per mole. And so that's what's going to go on the bottom right here, 44 grams of C3H8 in 1 mole. I know that 1 mole of carbon dioxide will always fill 22.4 liters, so I can fill that one in easily. And then I know that my gram to milliliter conversion is going to come from my density value, which is provided in the problem. So there are 0.5005 grams in every 1 milliliter of C3H8. And then last but not least, my mole to mole ratio is going to come from the chemical reaction, which we actually forgot to write down to start, so we'll need to do that now. So we know that burning is going to be a combustion reaction. So propane, let's see, propane, C3H8, is going to react with oxygen. It's a common mistake for students to forget the oxygen as part of combustion, but that is necessary for combustion to occur. It's always a reactant. And that's going to give us CO2 and H2O. And then we need to balance our equation to be able to figure out our mole to mole ratio. So I will just put some lines. Remember, in combustion, we never start with oxygen. We're going to start by balancing carbon and hydrogen. So to balance carbon, I'm going to put a 3 in front of CO2. And to balance hydrogen, I'm going to put a 4 in front of H2O. And then we'll figure out the oxygen last. So I always like to kind of connect my oxygens. So 3 times 2 gives me 6 oxygens from right here, and then 4 from over here for a total of 10. And then I need something times 2 that will give me 10, so that would be a 5. And then I'm going to fill in my 1 right here. So now we have our mole to mole ratio. So for carbon dioxide, we are going to put a 3 next to that. And then for C3H8, we'll put a 1. And now we have all of our numbers filled in. All that's left is to multiply this out and divide by what's on the bottom. So 0.25 times 1,000 times 0.5005 divided by 44 times 3 times 22.4. And what I get when I do that in my calculator is 191.1. But we do need to look at significant figures here, and given in our problem is just 2 sig figs. So 1 and 9 stay, and I'll look at that next digit over. So I will keep the 9 and 9, but 19 is not anywhere near 191, so I need to fill in a placeholder 0. So 190 without a decimal point, so no decimal point here, only has 2 significant figures, so I'll put liters of CO2. And then we'll just box in that final answer real quick. And there you have it. We've finished this problem.